In this lecture, we will assume familiarity with the following notions. A chain complex of abelian groups homology groups exactness of a chain complex short exact sequences of abelian groups snake lemma. So this says the following: if is a commutative diagram of abelian groups where the rows are exact, then there is an exact sequence where alpha bar, beta bar, alpha prime bar and beta prime bar are induced by alpha, beta, alpha prime, beta prime respectively. If alpha is an inclusion, then alpha bar is an inclusion. If beta prime is a surjection, then beta prime bar is a surjection. So we will also assume familiarity with maps of chain complexes. And such maps induce maps at the level of homology groups. short exact sequence of chain complexes and if we have a short exact sequence of chain complexes, then we get a long exact sequence, a long exact homology sequence. So if f dot and g dot from a dot to b dot are two maps of complexes, and there is a homotopy between them, then the induced maps on homology are the same. So all the above definitions and proofs of statements can be found in section 1 of the chapter on homology in the notes. So assuming the above simple complex concepts from homological algebra, we will define a chain complex C dot x for each topological space X, and the homology groups of this complex will be denoted by HNXZ or simply HNZ, HNX. So the main result we prove is that homotopy equivalent spaces have the same, have isomorphic homology groups. So we define the standard n simplex to be the subspace such that so this is delta 1, for example. This is delta 2. And more gently, we will also use the term n simplex to mean the following. Suppose P0 up to Pn in Rk are endpoints such that Pn minus P0, well, P1 minus P0, P2 minus P0 up to Pn minus P0 are linearly independent. Then the convex hull will of the PIs will sometimes be called n simplex. So we denote the vertices of delta n by Vni, where this is the vertex with 1 in the ith position and 0 elsewhere. So we define the ith face map so this is map Fni, let's say, from delta n to delta n plus 1, So we define it on the vertices as follows. So if j is strictly less than I, then v and j goes to vn plus 1j. And if j is greater than or equal to I, then v and j goes to vn plus 1j plus 1. And extend linearly. To all of delta n. So note that each point of delta n is a unique linear combination of the v and i's. So the image of fi, fni, is the unique face of delta n plus 1, which does not contain I, which does not contain bn plus 1I. So we now define a complex Cnx to be the free abelian group on all continuous maps sigma from delta n to x. In particular, Cnx is 0 for n strictly less than 0. So we define a differential from Cnx to Cn minus 1x by defining it on the generators and extending it linearly. And on the generators, define Tn sigma to be summation I equal to 0 to n minus 1 to the I. Sigma compose f n minus 1 I. So to check out the following proposition, shows that C dot x is a complex. So it suffices to check this on the generators. So let sigma from delta n to x, then Tn plus 1 sigma is equal to sum sigma compose Fni and En compose Tn plus 1 of sigma So here we have just applied the definition. So one easily checks for example by evaluating on vertices that Fn I compose Fn minus 1j is equal to Fn j plus 1 compose Fn minus 1 I when j is greater than or equal to I. So we break the above sum into two parts. So we get so if j is greater than or equal to I, then j plus 1 is strictly greater than I. Thus, for any pair k comma L with k strictly greater than L, the term sigma compose appears exactly once in both terms with opposite signs. Thus, Tn compose Tn plus 1 is 0. So we get a chain complex and the homology groups are defined as so these are called the singular homology groups. So let us see some easy examples. / computations. So proposition. Let X be a path connected space. Then H naught X is isomorphic to Z. Proof. Since C minus 1X is 0, it follows that kernel of D0 is all of C0X. Thus, H0X is equal to C0X mod image of D1. A map sigma from delta 0 to X simply corresponds to a point of X. Thus, C0X is simply the free abelian group on all points in X. So, let sigma from delta 1 to X be a continuous map. Then one easily checks that T1 of sigma is sigma of 1 minus sigma of 0. And since X is path connected, for any 2 points, P and Q, there is a path sigma from delta 1 to X such that sigma of 0 is P and sigma of 1 is Q. Thus, C0X by D1 of C1X is equal to modulo the subgroup generated by P minus Q, where P and Q are points in X. And one easily checks that this is isomorphic to Z. So another easy observation we can make is the following proposition. Let X be written as a disjoint union of its path components then n of X is isomorphic to the direct sum over alpha each n x alpha. So the proof, since delta n is path connected, for any sigma, this map factors as for a unique alpha. So from this, it follows easily that the singular chain complex of X is simply the direct sum of the singular chain complex of the X alphas. Thus, the same statement follows for homology. And finally, let X be a point, then H naught X is Z and HIX is 0 for I strictly greater than 0. So let us prove this. For any n greater than or equal to 0, there is only one map from delta n to X. Thus, for each n greater than or equal to 0, Cnx is simply isomorphic to Z. So let sigma n from delta n to X denote the unique generator. So then dn of sigma n is by definition Fn minus 1i. But each of these sigma n composed Fn minus 1i is precisely just sigma n minus 1. So this is equal to which is equal to 0 if n is odd and 1 if n is even. Thus, the chain complex looks like so in the 0th place we have Z, this d1, this degree 1, d2, this degree 2, and so on. And when n is odd, d1 is 0. When n is even, the d2 is 1. So d3 is again 0, and so on. And from this, easily follows that h naught x is z and hi x 0 for I. So next we want to investigate singular homology, the effect of continuous maps. So let h from x to y be a continuous map. Then it induces a map hn from Cnx to Cny by defining it as hn of sigma is h compose sigma on the generators and extending it linearly. So it is easily checked that hn compose tn plus 1 is equal to tn plus 1 compose hn plus 1, which implies we get a map of chain complexes and which in turn induces a map on homologies. And we also have the following functoriality property. So then, on the one hand, we have maps and on the other hand, we also have a map G compose F complexes, then G compose F dot is equal to G dot compose F dot. So the main result we want to prove is the following theorem. Let f from x cross I to y be a continuous map. Then f sub 0, which is the map from x 0 cross 0 to y, and f sub 1, so both are maps from x to y, can be viewed as maps from x to y. So induce the same maps on homology. So let us prove this. So we will define prism operators so Pn from Cnx to Cn plus 1y such that Tn plus 1 compose Pn plus Pn minus 1 compose Dn is equal to F1 n minus F0 n. So these two are maps from Cnx to Cny. So we have Cn plus 1x, Cnx, Cn minus 1x, and so on. So the prism operators are defined like this. So as always, it is enough to define Pn on the generators and check the above relation on the generators. Which is what we shall do. So we begin by introducing some notation. So let P0 to Pn in RL be points denote by P0 up to Pn up to PR. The unique map from delta R to RL, which sends PRI to PI and extends linearly. So let U contained in RL be any convex set and let P0 through PR be points in U. Let tau from U to Z be a map denote by P0 PR comma tau to be tau compose the map P0 through PR. So this is a map from delta R to U and then to Z. So with this notation, it is easily checked that TR of so pi hat means we don't include pi. Tau. And finally, for a point P in U, denote by P underline the point P cross 0 in U cross I, and by P overline the point P cross 1 in U cross I. So with this notation, we define the prism operators. At sigma from delta n to x, P a continuous map. Then notice that sigma can be written as Pn0, Pnn, comma sigma. So define Pn sigma to be equal to summation I equal to 0 to n So for simplicity, let us denote this by G for simplicity of notation. Let us denote by capital G. And it's clear that this is an element in Cn plus 1 y. So we need to compute Tn plus 1 compose Pn plus Pn minus 1 compose Tn. So when we apply dn plus 1 to the above expression, we get this is equal to so j runs from 0 to I first. We drop pj underline hat. So we drop pj underline. And plus so this time j runs from again from I to n, but minus 1 to the j plus 1. So this time we drop v and j overline. So on the other hand, Pn minus 1 compose dn of sigma is equal to so this is equal to so this time first we let j run from 0 to I minus 1. And the other terms are so this time j runs from I plus 1 to n. But now the sign is to j plus 1. So let's give these expressions some names. So let's denote this by 1a and this by 2a. It's 2b and this is 1b. So each term in 1b appears in 1A with an opposite sign. This is easily checked. So using this, it is easily checked that 1A plus 1B is equal to, so in 1A only the terms j equal to I will remain. Everything else will get cancelled off in the sum. And similarly, one checks that 2A plus 2B So using this, is going to turn out to be. So once again there will be a cancellation and only the terms at the ends will remain. So that will look like but this is exactly equal to f1 n of sigma minus f0. Let me write on the next page. So this proves that f1 and f0 induce maps which are homotopic. Which implies they induce the same maps on homology. So this completes the proof of the theorem. So using the above, as in the case of the fundamental groups, we get let f from x to y be a homotopic equivalence then f lower star from hix to hiy is an isomorphism. So proof. So let G denote the map. Let G denote a map such that G compose F is homological to identity X and F compose G is homological to identity Y. Then G low star compose F low star is identity on Hn X and F low star compose G low star is identity on Hn Y. So this implies F low star is an isomorphism. So we will end here. Before we end, so corollary of the above theorem, H0 of Rn is Z and Hi of Rn 0 for I strictly greater than 0. So proof for the corollary, the inclusion of let's say 0 into Rn is a homological equivalence.